So really when you are looking at radicals, your first property that you see here is if you multiply radicals, you multiply by what's inside. Very, very important part of this property is that they have the same index, all right? So as long as your index is the same, when you are multiplying them, you literally just multiply what's inside. And sometimes this actually helps you then get a number that you could simplify, all right? And so as long as your indexes are the same, you can go back and forth between these. You can take two separate ones and multiply them and get the answer, or you can split them out and do them individually if you want to, and break them out and do their square roots individually or your nth roots individually. All right, so let's look at this first one, A. They have the square root of 2 times the square root of 8. It is the same radical, so that is the square root of 16. All right, 16 has a perfect root, which is 4. So while 2 and 8, neither one of those had a perfect root, when you multiply them, you actually got something that did. So your answer here would be 4. When you look at B, cubed root, these are both cubed, all right? So we are going to say the cubed root of 5 times, or negative 5 times positive 25 is the cubed root of negative 125. That does have a perfect cubed root, which is negative 5. All right. Let's look at C. Square root of negative 2 times square root of 8. If you go back up here, if the nth root of A and the nth root of B are real numbers, then you can use this property. What's the problem with this question? This guy is not a real number, right? He's a complex number. So the property doesn't apply, and you don't have an answer there. Does not apply. You cannot multiply these. The property says that they must be real to apply this. They are not real. You can't use the property, so you can't multiply them. All right? The difference between this, I multiplied this guy. I couldn't multiply this guy.
Because it's to the third?
Yeah, it's to the third. This is a real number. The cube root of negative 5 exists in the real number balloon of numbers there, right? This guy doesn't. He is in the complex, and so it has to work for real numbers only. The way they show it in the book actually requires that you kind of know and can recognize your perfect squares, cubes, etc. Which for maybe a square root, that's easy. I mean, you might be able to easily see that 72 is 36 times 2, all right? But if this were like a much larger number, like in the hundreds, you may not see a perfect root in there, okay? So if you can see a perfect root, you can certainly use the principle of, well, that's 36 times 2. The 36 has a perfect root. Take out the 6. I have a 2 left over, okay? The way I teach it is just to always do prime factorization, okay? Always do prime factorization. Your index tells you what type of grouping you're looking for, and then everything else stays in if it doesn't group in that order. So like for this one, for this particular one here, I would say, well, I'm going to do my prime factorization for 72, right? And I'm going to always start with a small prime, 2, 3, something like that, 2, 3, 5, okay? 2 goes into it, obviously. 2 goes into that again. 2 goes into that again. 2 goes into that, or 3 goes into that, right? Okay. What is my index for this guy? What's my index? My index, 2, right? So I am looking for everything that groups in pairs, all right? If it groups in 2s, it can come out as 1, all right? So it groups inside, the way the index tells you, it comes out as 1 number, okay? So 3, I have 2 of those, so a 3 can come out. 2s, I have 2 of those, so a 2 can come out, all right? And then I have this little 2 that does not group. He must stay inside my radical, all right? So he's going to stay in there. For the variables, I just use division, okay? I use division. So what I'm going to do is I'm going to take this x cubed and I am going to look at the exponent. And I'm going to say, well, 3 divided by my index, all right? So we're going to divide the exponent divided by the index. What is my index again? 2. 3 divided by 2. 2 goes into 3 how many times? one time with a remainder of 1. All right, everybody agree that's how you divide 3 and 2? All right. This tells me what comes out or how many of them come out. My remainder tells me how many stay in. Okay? So that means I am going to have 1x come out, and I am going to have 1x stay in. All right? If multiple things come out, you multiply them. If multiple things stay in, you multiply them. So my final answer here to simplify this is 3 times 2 times x, which is 6x, square root of 2 times x, which is 2x. All right, now I will say that when we did this one, they did not do this in their answer, but I pulled out an x to the first power and my index is 2. All right, my index is 2. So you may want to put your absolute value there, right? If I were just doing this as an answer, what would I need to do with that x? X to the first can be negative, right? So for everything that I do for you, I would say to do this guy right here, okay? Because there's an index of 2, exponent of 1 on the outside. I'm going to take my 80. I'm going to do the same thing with my 80, 2 and 40, right? All the way down. Okay. What's my index here? 3. So when I group these, I have to group them in 3s. I have 1, 2, 3 2s. That group can come out. All right. 2. He does not have another group of 3, so he's staying in. 5 does not have a group of 3, so 5 is also staying in. All right. They both stay in. Let's look at my into the 5th. I'm going to say 5 divided by 3. How many times does 3 go into 5?
3.
1 time with a remainder of 2. So that means I am going to have 1 in that will stay, that go out, 2 n's that will remain inside. So I have n to the first out here, n squared in there. And so my answer, when I simplify that, is going to be 2n cubed root rather, of 10n squared. I will say, make sure this guy makes it to your final answer. That is a pain when you miss points for not putting your index in your final answer. All right, multiply and simplify, assume they're positive, so they are assuming these are positive again. All right, I will say, when I do multiplication like this, I do combine my variables before I multiply, but I actually don't combine my numbers. There's a reason for this. So like, I will say 54 times 5, but I'm getting ready to do prime factorization. So why would I go ahead and multiply to just divide it back out? Does that make sense? So I'll actually just write the 54 times 5, and that number is whatever it is. I actually don't care. I don't care what those equal, unless for some reason nothing comes out. For my x's then, x squared times x to the 3rd, that is x to the 5th, right? Y cubed times y to the 4th, that is y to the 7th. But I don't multiply by numbers yet. because there's no reason to. I'm about to factor them out. So you can just think of those as your first two factors of whatever number that guy was. All right, and then you can factor from there. And so I would continue factoring. 54, well, that's 2 and 27. That is 3 and 9. That is 3 and 3. All right, so my factors would be 2, 3, 3, 3, 5. Okay, those are my factors, whatever number they equaled, right? For my 5, I'm going to do, I now remember my index is 3. So my 5, I'm going to do that with a 3. My 7, I'm going to do that with a 3. All right, so my index is 3. So I'm going to say, okay, these pair up as a 3. Those can come out. We'll put those out. The 2 and the 5 do not pair up in groups, so they're going to stay in. So 2 and 5 are going to stay in here. And then I'm going to do my numbers the same, my variables here. So 5 divided by 3, well, that's 1 with a remainder of 2. 7 divided by 3, well, that is 2 with a remainder of 1. So for my x's, 1x is going to come out. 2 x's are going to stay in. For my y's, 2 y's are going to come out. 1 y is going to stay in. And then I'm just going to simplify 3 times x times y squared. Make sure you put your index 3. 2 times 5 times x squared times y is 10x squared y. Make sense? So you've already started your factorization if they've given you numbers to multiply. And just make sure you include all of them. Like, don't forget him, that he was one of your prime factors. Because that could also be a 12. It could have been 54 times 12. And then you would have had to factor tree both of them and count all of their prime factors in what you're deciding goes in and comes out. Okay, so go ahead and try. And really quickly, because the example they give you to do, the 3 and the 2 are already out, so they stay out, multiplied. 3 times 2 times whatever you're pulling out, okay? They just stay out because they're already there. You just multiply them together along with anything else you pull out of your radicals. If the nth root of A and nth root of B are real numbers, once again, they have to be real, and B does not equal 0, then when you divide those two, it's just the same thing as taking the fraction and using the nth root of the fraction itself. So you can either do the roots individually, or you can do the root after you have divided it. Sometimes dividing it first helps. Sometimes taking the root first helps. It just depends. They do both have to be real, and your denominator cannot be 0, which is true of all fractions, okay? So if you look at this first one, the cubed root of 32 divided by the cubed root of -4. Neither one of those have a perfect cubed root. But 32 is divisible by 4. So for this one, it's going to be more simpler if I divide first. So I would take this and I would say, well, let's just do the cubed root of the division. All right, what is 32 divided by -4? -8. All right, so I have the cubed root of -8, which does have a perfect cube of -2. Okay? Let's look at the next one. Cubed root of these two. I have 162x to the 5th, 3x squared. All right, is 162 divisible by 3? So yes, 162, by the way, is divisible by 3. 6 plus 2 plus 3, plus 1 is divisible by 3. So I can divide those first. What is 162 divided by 3? 54. And then what is x to the 5th divided by x squared? X cubed, all right? 54, so 54 doesn't have a perfect root, right? But I can use my factor tree. That's 2 and 27, 3 and 9, 3 and 3. So my 3s do pair up in 3s, so that can come out. This 2 does not, so that is going to stay in. All right, and then this guy, we have 3 divided by 3, which is just one remainder of 0. So I have 1x that comes out, 0x's stay in. And that would be my answer there. All right. So rationalizing the denominator is just getting your radical out of the denominator. So when you rationalize the denominator, you are just getting a radical out of the denominator. It's almost like leaving something in not lowest terms. Like you wouldn't leave this guy as your answer. Well, some of you would, but you would get counted off for that, right? Like, no, don't do that. And so same thing comes with radicals in the denominator. They're typically not looked at as completely simplified if you have left a radical in the denominator. I will say sometimes in higher math, like even in your calculuses, sometimes they leave it there because they're just going to move on and do something else and go into decimal form anyway. All right. But when you're actually leaving your answer in simplest radical form, you don't want a radical in the denominator. The way you get rid of a radical in the denominator is just multiply it out. So if I won't have the square root of 5 down there, I'm going to make that into something that has a perfect root so that the square root of 5 is gone, right? Which means I'm going to multiply by the square root of 5, which is the square root of 25, which gets rid of it. However, I have the cube root of 5. I would have to do that 3 times, right? I'd have to multiply by the square root of 5, square root of 5, right? To get rid of it, because that would be the square root of 125, which has a perfect root, all right? So you have to look at how many times it's down there and how many times I need to do something to get rid of it. Whatever I do it to a denominator, I have to do it where? In a fraction. Numerator, or I have changed the fraction. So if you are rationalizing the denominator, whatever you have to do to rationalize it must also be done to the numerator. Does not matter if a radical is in the numerator, you are only rationalizing the denominator. So let's look at this first one. If I have square root of 2 over square root of 3 and they want me to simplify this, the square root of 3 in the bottom can be gotten rid of by just multiplying by square root of 3. If I do that in the bottom, I have to multiply the top. All right, so square root of 2 times square root of 3, that's simple, square root of 6. If I multiply a square root of 3 times a square root of 3, I get a 3, and that is as simple as it gets. You cannot simplify inside to outside. So I cannot simplify that 3 and 6. One is inside the root, one is outside the root. So it is not a 6, it is a square root of 6, which is not divisible by 3. The square root of 6 is an irrational number, not divisible by 3, okay? So only in the root can simplify. Let's look at the next one. Now I will say for this one, don't forget that in the root, you can simplify, okay? So before I do this one, I am gonna potentially simplify it before I rationalize it, all right? Because if not, then I'll have to simplify at the end. So looking at this, they're both in the root. What can I simplify? The x's, right? So this can become x squared, and that guy can go away. So I have x squared over the square root of 5y now. And once again, I can rationalize by just 5y, 5y. And I am going to get the square root of 5x squared y over just 5y.